As we have already improved the mesh quality, and therefore we will now go and open Fluent. So from search bar on the Windows, type Fluent, and this will give you the full name, and then simply click on enter key on the keyboard, and this will open Fluent, and make sure that the 3D option is selected, and the number of cores in my computer are 4, so therefore I'm selecting them 4, but for these number of nodes, which are almost 0.12 million, the 4 cores are more than enough. So I can also run this case on the 2 cores, and if you have the 1 core only, then you can run also case on the 1 core. The rule of thumb is that for every 0.25 million nodes, you should have the 1 extra core. So if there are the 0.5 million nodes, then you should use at least 2 cores, and for 1 million nodes, at least you should use 4 cores. So therefore I'm using the maximum cores I have, and then click on start. And also I have enabled the double precision solver here, and my working directory right now is my F drive, where I have all files, but you should make your own working directory where you have all the files in a very arranged format. So always make your work very organized, and make the folders, subfolders where you save your files, everything. So now click on start. And from file menu, click on read and mesh. And I told you in the last video that I will modify my mesh file name, which is here. So I will rename this file, which is the existing file with the mesh problem. So let me change the name to problem ortho quality. Okay, so I will keep this file with me, and in the coming videos I will show you that if we run this file and this file, then what will happen. And also, if you notice that this file has more number of nodes as we defined the mesh in the model layer, and also in the free stream blog. So this might be, it's not exactly a mesh dependent study, but because the number of nodes are changing, so you might see that if this will affect your mesh, if this mesh will affect your results or not. So that's why I'm keeping this file with me, and also I will upload this file, and you will find the files in description of video. And therefore I will now open this file. And for second file, I will not show exactly all steps here, but you know how to import that file if you know this file, this work here. And I will also show you that how you can keep the same thing, everything in the Fluent, and just change the mesh. And that is from this menu domain and replace mesh. So this replace mesh is a very good option, where you can just replace a mesh, and every setting will be there inside the Fluent. And first thing is that we will keep the pressure base, because we are going to solve this case as the incompressible flow. And in the models, and as this flow is incompressible, there is no need to turn on the energy equation, because we will model density as the constant value. And the viscous, we have by default we have the SST model. You can use K omega or Estrada Almaris, or also you can use a K epsilon with residual option, and use an enhanced Wahl treatment, because y plus is equal to 1 less than 1. And I would prefer that we should go with the SA model or SST model, or we should go with the transition SST or transition K and omega. And in the coming videos, I will show you that in this case, in this Airfoil NACA 0012 at 3 million Reynolds number, we have some portion of the flow on the leading edge is laminar flow, and then it will transit into the turbulent flow. So if you don't solve that flow, if you don't simulate that portion of the Airfoil, especially at 0 angle of attack, so you will get the error in drag coefficient as much as 100%, which if you take a look on my simple Airfoil mesh, the 2D Airfoil mesh which I created like 6 years ago, you will see that in that case we have very much large error, and that is coming from when we don't model the proper turbulent and laminar regions, and we get that issue. So right now I'm going to use the Spiral-Armas method turbulence model right now and click on OK. And in the materials we have the default conditions, and if you take a look on this Excel sheet, and if you recall, this was used to calculate the first cell height, and I told you that we will use these values, density which is 1.225 and this 0.40 and 1789. So approximately if you round off, this is 179. So we'll keep this value here and click on change create. And the next thing we will change is the velocity here. So I will go into boundary conditions, and also we will confirm that every boundary condition is correctly specified here. So 40 meter per second, and no thermal boundary condition here because there is no pressure here. And you can also specify the magnitude and the direction. So if you do it, then in this case, and now just let me display the mesh file, and if you take a look here, and I will also enable the display edges, and from here I will choose the rotation tool like this. And if you press the control key, even if you have the pen option, and if you press the control key, you can move it in this way, and with the middle mouse button you can rotate it, and also with the middle mouse button with the wheel you can zoom in or zoom out. So if you take a look here, you can see that we have this mesh in this way, and the direction, third direction is the Z direction. So there is no change in the flow component Z direction because that is when we have the side slip, and for angle of attack that is alpha angle. So beta angle is always in the Z direction, but for the alpha angle, which is the angle of attack, we will provide in the X and Y component. So X will have the cos component and Y will have the sine component. And if the angle of attack is 0, so sine 0 is 1, so X is 1, and the Y is a sine 0 is equal to 0, and there is no side slip component, so Z will always be 0 here. And then click on apply, and just for your information, let's say if I want to solve this case at 4 degrees, so 4 cos will be equal to 0.9975, so I will put this one in S component, and again the 4 of sine theta will be in the Y component, so 0.069 and 75. So I will just keep this value here, and I will just make sure that my interior fluid is the interior, and aerofoil is the wall condition, outlet is the pressure outlet, and symmetry is the symmetry 2 is also symmetry. And also important thing is that we have the operating pressure, and that operating pressure should be same as the 101.325. This is the pressure of that atmospheric condition. So we are simulating this flow at the sea level. So I will keep this value same here. But when you solve the flow as a compressible, in that case we will make it 0, and we will provide this pressure in the inlet condition, where we will define as a free stream Mach number and the free stream operating static pressure, and at the outlet again we will define the same static pressure here. So right now just keep the things same as they are default, and then I will choose a method. So again we will keep the default method, which is coupled, and coupled is a very good method for when the flow is compressible or incompressible. So in both regions this will work very fine. And the important thing is that this will couple your continuity equation, momentum equation. So this will take less iterations, less number of loops to solve your case up to the convergence. And I will leave it as a pseudo transient. And for the first iteration you can use further up, and then after 15 to 20 iterations you can change it back to the second order. So I will keep it first order first, and then I will change it to the second order. And then in the monitors, so for the monitors you can especially for residuals, I will put the values to the 10 power minus 6 or less value, so that I can solve this case up to number of iterations I require here. So I will usually run it longer time so that we can have the surety about convergence. So I will keep this value very low and okay. So you can see the minus 8, minus 7, so it should be less than minus 6. And the report definition, that will be, you can set them in a one go, these report files. These are text files, you can open them in Excel as well, and you can plot them again, those parameters like the drag and the lift coefficient versus number of iteration, number of time step for the transient solution, and report plots. So that can be defined in a one go from report definition. So right click on report definitions and new, and we are going to plot the surface force reports, drag and lift. So from here we have the first one is the drag, so I call as a drag coefficient, and on the whole aerofoil, this is 3D aerofoil, but because we have symmetric conditions, so on the two sides basically this is the infinite type of the aerofoil here. And for the force, for the drag coefficient, which is always in the direction of the flow, so it's a 0 angle, so x will be 1 and y will be 0. And report file will be generated for every iteration and print to console. And you can also make it as a create output parameter, which will be shown in the workbench if you are creating this project in the workbench. So this will be shown as a output parameter on the workbench. But because we are solving this case as a standalone case, so I will not make it as output parameter, and click on OK. So we are done with the drag coefficient, and in a similar way I am going to make a lift coefficient. So lift, and this will automatically change the x to 0 and y to the 1, because the lift is 90 degrees to the lift, to the drag coefficient. So 90 degrees means that the cosine 0 will be a 0, and sine 90, cos 90 will be 0, and sine 90 is equal to 1. Again we will take the report file, report plot, and print to console, and choose this NACA 0012, and I put the name as a lift coefficient. Short form of coefficient is COEFF, and we interested in the lift coefficient, so I will not choose the lift force, and click on OK. Okay, before going for these monitors to work, we need to set the reference value. So in the reference values, first of all you have to compute them from inlet, so it will take the many values automatically, like the velocity, the viscosity, and density. So these all will come from the inlet. The only thing I need to provide is that, because in this case the chord length is 1, right, but in the z direction we put the value as 0.3. In 2D aerofoils we assume that the depth is also 1, so therefore the area is kept as the 1 meter square. But in this case, because now the length is our chord length is 1 and the depth is 0.3. If you remember, when we created this geometry, I told you that for turbulent simulations you can minimize the domain extent in z direction, and rule of thumb is that the minimum dimension you need is a 0.3 times the chord length. So we put this length is a 0.3 of chord length, which is 0.3. So area should be equal to 0.3 meter square. So length is 1, which is correct here, and everything else should be kept same. So only thing I change here is that we put the area as a 0.3 meter square. And now again go back to this left side tree, and from here I am going to initialize solution, and we will use hybrid initialization. This will give you the initial conditions with the help of the potential function. So it will not solve the flow as a viscous flow, but it will give you some solution which will be the very much accurate for the initial solution here. Now you can see that this will make the 10 iterations, and its goal is that it should be reduced to the -6 or low values. So after this is finished, we will run the case, and before that I will save the file with the same name, So I want to save in the standard case and data file. So these are the new names, which are the H5, and click on OK. This is very important because these all settings will be saved in this file, and in case of the file the power failure or any issue, you can get the back file and again you can run the case. So I will run this case for the 500 iterations. This is more than enough here, and click on calculate. After running around 40 iterations, I am going to stop the solution, and you can see the drag coefficient convergence and the lift coefficient convergence. And typically speaking, for the zero angle of attack, you should not get any lift coefficient for symmetric aerofoil like the NACA 0012. But I will see that what is happening here. But before that, I will go to the controls methods, and from here I will choose the second order scheme for the momentum equation, and I will continue solution from here. So, and before that I want to save the file on the same name, and then click on calculate. We are going to now stop the solution here. As you can see that the residuals are converging and they are in a straight line, and so the drag coefficient and lift coefficient, and if you observe, they've achieved the straight line in within 40 iterations, and drag coefficient also within the 30 iterations or 20 iterations, less than 20 iterations. So I'll stop solution here, and the only thing I can see that the drag coefficient is little higher, which is very common for turbulent, fully turbulent simulations, and this is same you will find everywhere. This value of drag coefficient, which is 0.0096, and the actual value is somehow different, and there's error of more than 50%. I will discuss in the next video along with NASA reports, and in fact NACA report on the NACA 0012 aerofoil at 3 million Reynolds number at zero angle of attack. And also I will show you how to compute. This result is coming from these monitors, and there is a special menu or special tab for the determining the forces like the drag coefficient and lift coefficient, drag force and lift force respectively. So we'll discuss all these things in the next video, but before that I want to save the file, and just put the name NACA 0012 3D and click on OK. And these files will be saved here. You can find them here. All output files are here. Mesh file is, both files are here. These are H5 files, so these are single files. And we must find out the okay, so we don't have any other option instead for the H5 format, so we have the H5 at the end of the case and data file. So anyhow, this is the latest file we have here, and in the next video I will open the same file, or I will not close in fact the Fluent app here, and we'll discuss about the results. But before that I want to say the last comment on this video. The lift coefficient should be 0. It should be 0. Why? Let me show you. This is from NASA's website, and you can see that we have the drag coefficient and the lift coefficient against angle of attack, which is the alpha, and so CL, and this is CD versus CL. So, and this is Reynolds number at 3 million, and you will see that so let me first confirm Reynolds number is 6 million. Okay, so in any case, because this aerofoil is symmetric aerofoil, so at zero angle of attack for any Reynolds number we should get the CL is equal to 0. and since we are not getting a 0, so we have to investigate further that what is happening here. And so in the coming videos, before first we will discuss the CD coefficient, and then we will discuss about the CL value, and then finally we will discuss about how to correct the CD value, or to how to correctly predict the CD value for this Reynolds number at 0 angle of attack. But before discussing about the CD value, we will look for the solution for making the CL is equal to 0.